Hey, what's up, guys? Chung here again. So this time, uh, I want to talk about this 239 sliding window maximum. It's a hard problem, but it's not that hard actually. But I still gonna give it my own upvote. Since if you guys saw my previous videos, so this this problem is just part of that even harder problem. But anyway, let's take a look. So you're given like an array here, right? You're given like an array and and a case and a sliding window k basically. There's a sliding window k moving along the array here, and they ask you to find out what's the maximum number. Yeah, basically what's the maximum number you have seen so far, right? So it's a and it gives you like the length is like 10 to the power of 5, right? So which means we can only solve this problem in either n log n time or or n or o n time. Anything that's above n log n, for example, n squared will be TLE, will be time limit exceeded, right? So so actually the key point is the how can we efficiently find the maximum number within the case sliding window, right? Uh, a very intuitive way is to use a priority queue, right? Basically, we maintain like we use a priority queue to maintain the biggest number we have seen so far. Basically, what does it mean? It means that every time when we move the sliding windows uh one one position to the right, we first try to update the sliding window. So to update the priority queue by removing this element, right? By removing this element from the priority queue. Basically, if this one is the highest number, is the first element in the priority queue, right? Then we know, okay, we lost the the biggest number, right? We simply just remove it. We simply remove it from the pop it from the priority queue, right? And then every time when we have like a bigger number here, we also update the priority queue, right? By actually simply push the new element into the priority queue, right? And the priority queue will maintain the biggest number for us, right? And we can also pop, right? If we want to keep this priority queue relatively small, we can every time we have a new numbers here, we compare, right? We compare if this one is bigger than the current biggest number. If it is, we pop it out from the priority queue, right? So let's try to implement this priority queue algorithm first, and then we'll go to this log n solutions later. So let's do a answer here, right? And priority queue. So for I equal number numerate nums, right? And since we have this sliding window here, right? So we hmm, uh So first, if I is greater than k, right, that's when we need to discard the element, right? And priority queue, the first element is equal to the element it's about to move outside of the I minus k, right? So if it's 3, right, then we're at like 0, 1, 2, 3, right? And 3 minus 3 is 0, and which means the 0 is the one that's going to be moved out, right? So we check if this the one that's being moved outside of the sliding window is our current biggest number, right? Then we simply do a pop. We do a heap pop, right? Heap pop with the priority queue, right? Otherwise, right? Otherwise, what do? We simply do answer, right? Dot append. Sorry, if I greater than k, okay, do an answer dot append. Append our heap queue, right? It's always the first element. Oh, no, sorry, we move this thing out of the sliding windows. We also need to add our current value. Add our current value into the priority queue, right? Which is the we can simply do a heap queue dot heap push, right? Priority queue and number that will give us the current biggest number, right? Thing here, yeah, we can just simply do a push, and then in the end we just return the answer. I think this should just work if I didn't do anything wrong here. Oh, sorry. So heap queue push, right? Since we're going the in Python the priority queue is a mini heap, so we need to do a convert it to a negative value, so that can give us the the maximum. Oh, sorry, k minus 1. Uh, let's see. Yeah, I think here it's I made a mistake. So since we're converting everything, every time when we try to use this one, we also need to convert it to a negative value to compare with the current value, right? Otherwise, we won't be able to do it. Uh, come on. Yeah, I think one mistake I made here for the priority queue is that not only I need to store the value, but also I also need to store the index here because here, right, here we're not when we try to update the priority queue, right? So basically we should not only comparing the numbers here because even though the so basically here, right? So here uh we should also store the index because every time when we move one index out of the sliding window, we have to pop everything out the biggest number that's before this index, right? That's why we need to do a I here. Same thing. Uh, and we instead of if, we're gonna do a while loop because in this case there are like two nines, right? There are two nine here, and when we reach seven here, minus seven here, we need to pop both of them outside of the priority queue. If we only do a if here, right, we'll be basically we'll be only popping one out of it. That's why we have a nine left here because we only pop one. So what we need to do here, we have to do a uh, while yeah, we also want to make sure the priority queue is not empty, right? And one, right, smaller equals smaller than the I minus k, right? Basically everything that's smaller than this I minus k, we need to pop them, right? Here in the end we simply return zero here, right? I think that should work. Uh, Not minus, yeah. Since this index is just a positive thing, we don't care about the either negative or positive, just that. Cool. Finally, yeah, pass. Basically, with this priority queue, right? If there is like a duplicate numbers, right? If there's duplicate numbers in it, basically we need to store not only the numbers but also the index because every time when we move when we uh uh move some element outside of the uh of the sliding window, right? We will we want to move everything before that. For example, there's a 9, 10, and 9, right? So when we move 9 out of the sliding window, right? And since the first one is 10, right? Since the and in the priority queue, the first element is 10, and we see the 10 is not has not been moved outside of it. So that's why we will be maintaining 10 in the element in the priority queue. Basically, we're not removing anything, which means the 9 is also in the priority queue. And then when we reach 9 here, when we reach 10 here, right? When we reach 10 and then we see, okay, we have a 9, right? We remove 10 out of the priority queue, and then the next one will be the 9 here, right? If we see 9 here, do we have a yeah, that's why we want to sort this I in the increasing order. In case of we have a nine, two nines, we want try to check this I which has a smaller value. We see okay, so this 9 also has a smaller value than the I and the K. And then we also remove this 9 out, right? And then this 9 and that, right? So okay, yeah, that's the priority windows. Sorry, the priority queue. What priority queue? And the time for this is unlog n because each time when we do a heap pop or heap push, it's a log n time, and we need to do this for n numbers, right? And that's why it's a log n method. And now the n time, the on time solution here, right? So for on solutions, we're gonna use the monotonic queue, right? And since we need like the to maintain to get the maximum number in this case, right? That's why we need like decreasing queue. Okay, so let's do a decreasing queue here, right? Uh, okay, so answer same, and then decrease queue. Okay, uh, collections dot dq, right? Summarize the priority queue and enumerate numbers, right? So let's see. So for the DQ, first we also need to update our queue, right? We also need to update if the current uh, if the element that's being moved outside of the slider window is a current is the biggest value, right? If it is, then we just pop that thing. And so for the for the decreasing queue here, uh, we don't need to do a while loop here to comparing with the index here because the when we maintaining this like a decrease queue, right? Let's say for example in this case, right, when we see a 9 here, it's in the queue, and when we see a 10, since 10 is greater than 9, and then we will simply remove 9 from the decreasing queue, right? So for that for that reason, uh, we don't need to worry about anything, any like invalid number that's still stuck inside this decreasing queue, not like the priority queue. So in the priority queue, since we always do a push, and that's why when we see a new uh, we find a new index here, right? So we will basically try to remove everything that's before that index, before the index that's outside of the sliding window. That's what makes this uh, the mono queue. It's a better data structure for this kind of problem, right? Basically, in this case, all we need to do is we can simply track if the current if the element is being moved outside of the sliding window is the biggest one, right? We can either save the index or the values in this like mono queue. And let's see, I'm gonna do an index at this time, I think. So basically, if the same, if I is than k, right, and q dot zero, the first one is the one that's being moved outside of sliding window, which is the k minus I minus k, right? You can since here I'm saving the index, that's why I can simply compare the index of the current one. If if the values, you can simply do a num, right? The value here. Either one is fine here. The only thing is that for the num, you will be having you might be having duplicate values in this uh, decreasing queue here, while for the index, every element in this decreasing index this decreasing queue is unique. And so and that decreasing queue dot pop left, right? Since the first one is the biggest one, and then we're gonna update, right? And then we're gonna updating this like decreasing queue by inserting this current one to the decreasing queue here, and if the decrease queue dot the last one is smaller than the current number, right? We pop it. Sorry, we pop this decreasing queue, and in the end, we just do a insert, append this number, append this index, right? Index, since we're doing yeah, that's why if you do a index here, right? So you have to do a num here, nums, since we're storing the index, right? That's why if you're storing a value, you can simply use this one to check this. And then now the answer, right? Append, since it is the index, so that's the nums I, right? Sorry, num, sorry, q dot 0. That's our current max value, right? Simply return the answer here. Okay. Yeah, sorry here. If I is greater than k minus 1, right? Since we are only caring about when there's enough value in the range window. If hasn't range if we haven't seen that window yet, we simply do not insert. All right, cool. So yeah, basically this is the mono queue solutions. It has a advantage than the priority queue. The implementation is a little bit different, but I think for the priority queues, you have to basically also store the index because you're not every time you do a push, right? You do a push and let's see. I think, yeah, okay, let me do a quick uh, changes there. I think I find another way of doing the priority queue. So I'm gonna comment this thing out. So basically, and just similar like the priority queue, how we update the mono queue for the priority queue here, and we can simply do a if here, right? We keep this thing here, and we still do a if here, but while we're pushing it, right? Before doing that, just like the mono queue, we also do a check, right? If the priority queue and the priority queue, uh, basically we check if the current one we're pushing in is bigger than the current, is bigger than the current one in the priority queue, right? The first one, then we just pop that thing out. Basically, that's the if the number, right? If the number, if the minus 0. Yeah, I think for that we don't even need to store the index here. We can just simply we can just simply use the same approach as the queue here. And okay, let me try to finish this thing here. Okay, you know what? Forgot what I was talking so about. So for this like priority queue, we still need to do a while loop to remove everything that before that index. So okay, then the queue here, the mono queue. This is like a more efficient way of finding the minimum or maximum values within a sliding window, right? We do it by first update the queue to check if the element going to be is moving outside of the sliding window uh, is our biggest element or not, right? And if not, then we just add this thing. We add the current one to the sliding window here, right? Because the reason we can add this thing here is because since we're getting the maximum, right? So like I said, so anything that before this like bigger number will not be considered as a maximum number anymore, right? Since we have this bigger number also has a, a bigger index, which means this number will be moved outside of the sliding window later than all those previous smaller numbers. So those previous numbers are useless. That's why we can safely remove them out of the decreasing queue. And then we just simply and then we once we finish updating the mono queue, we simply just use whatever in the front to append to our final answer. Okay. Uh, yeah, I think that's it for this problem. Yeah, I hope you guys like the videos. Thank you so much for watching it, and I'll try to do a few more mono queue problems in the futures. And stay tuned. Thank you. Bye.